In this video, we're going to go over the solution to the Chapter 3 in-class problem number 4. In this problem, we're dealing with a piston cylinder and a gas inside that piston cylinder. The gas is initially at a temperature of about 500 degrees C, and the cylinder itself is at an initial temperature of 50 degrees C. Both the mass of the gas and the mass of the cylinder are MA and MB respectively. Now in this piston cylinder device, we're not concerned about expansion or compression or things like that. What we're more concerned about is the heat transfer that occurs in this system. And so heat is going to travel from the gas to the piston cylinder at a rate described by Newton's law of cooling here, where H is the heat transfer coefficient, A is the contact area between the gas and the cylinder, and TA and TB are the temperatures of the gas and the cylinder, respectively. Heat not only travels from the gas to the cylinder, but heat also travels from the cylinder to the surroundings outside the cylinder as well. And it's described by a similar equation here, where T naught is the temperature of the surroundings. We're also told that the heat capacity of the gas and the piston are CVA and CVB, respectively. And so based on this premise, what the problem asks us to solve for is to first derive a set of differential equations that describe the temperature of the gas and the temperature of the cylinder as a function of time. And then in parts B and C, we're asked to solve for both those temperatures by making assumptions about the product of the mass of the cylinder times its heat capacity. And so based on this, the text in this problem statement, I want you to pause the video and go out and draw a schematic describing this system. And so from this problem statement, we can identify that this problem basically wants us to figure out what the gas and the cylinder temperatures are as a function of time. Right? And so here's a schematic of what we can imagine the system to be like. And so we have a piston cylinder system where inside the cylinder we have a gas, and so I'm going to call that system A. And then for system B, we actually treat the piston cylinder itself, so all the metal parts of that piston cylinder setup. Okay, and I'm going to call that system B. The A here, this is going to be the interfacial area between system A and B. And then also, for simplicity, just for this specific problem, we're also going to say this is the interfacial area between system B and surroundings. Okay? And so this is just to help make the algebra easier for this example. All right? In any case, so we have a gas inside the piston cylinder setup, and the gas is initially much hotter than the cylinder is. And so heat is going to transfer from the gas to the cylinder, but then heat will also transfer from the cylinder to the surroundings as well. And so the heat is described by the Newton's law of cooling, where H is going to be that heat transfer coefficient, and then T is the surrounding temperature here. And so to at least write all this down, at T equals 0, we have that the temperature of the gas is equal to some initial temperature, and the temperature of the cylinder is also equal to some initial temperature as well, which coincidentally is also equal to the surrounding temperatures. Okay, and so this is where TA naught is going to be greater than T naught. Okay, and so heat is going to travel from A to B, and also heat will travel from B to the surroundings. Where the heat that goes from A to B is described by this equation, and the heat that travels from B to the surroundings, which I'll call S, will be this equation. And so our goal in this problem is we want to develop an equation that describes TA and TB as functions of time specifically. And so what that means is that we're going to need to solve, two separate differential equations. Separate differential equations. Okay. Now, before we start, applying our balances and trying to solve for these temperature equations, we need to apply some assumptions. Okay. And so, based on the text of this problem, there doesn't seem to be any work going on. Even though we're dealing with a piston and cylinder, once again, we're not looking at any sort of expansion or contraction. We're just looking at heat transfer. So there's no work going on in our system. So we'll say our differential work is going to be equal to 0. Okay? And also, we're not going to care about any changes in potential or kinetic energy. Okay? Now, for parts B and part C, it does ask us to make some assumptions about the product of MB CVB, but we're going to talk about those assumptions when we get to those parts. Okay? In any case, these are the main assumptions that we're going to work with. And so at this point, we could start applying our balances. And so let's start with the material balance for system A. So we have accumulations equal to input minus output plus generation minus consumption. There's no reaction going on here. And also, this is a closed system. Right? There's no mass crossing the system boundaries. So that's also equal to 0. And so we get that our accumulation is equal to 0. We could also write accumulation in terms of final minus initial. So this tells us that the initial amount of gas in the system is equal to the final amount of gas. Okay? And so, or in other words, our initial amount of gas, since it's some MA naught, is equal to some MA final, which I'll just call MA, just to simplify things out. Okay. Similarly, if we did the material balance on the piston cylinder itself, we would also get that the cylinder's initial mass is equal to the cylinder's final mass, which we'll just call MB. Okay. So those were the material balances. Let's now move on to applying the energy balances. So for this, I'm going to go to the next page. All right, and so for the energy balances, once again, what we're interested in is to develop the temperature equations as a function of time. So we specifically care about how the temperature is affected by time. And so for that reason, for the closed system, what we want to use is the rate form of the closed system energy balance. So starting with system A, we could write out the closed form, or the rate form of the closed system energy balance. Q dot plus W dot. Now we can apply our assumptions. So there's no work going on in this system, so that's going to be equal to 0. And there's no changes in kinetic or potential energy that we care about. So those are also going to be 0. Okay? And so what we're left with is that the change in the internal energy of the gas, system A, is just equal to some sort of heat flow rate. Okay? If we take a look at the internal energy for the gas, we could write it in terms of its heat capacity. So d MA, I'm going to keep it in mass here. And the heat capacity for A, this in on a per mole basis is this. And the temperature of A is also in here. So once again, this just comes from the definition of the heat capacity. Right? We know that the heat capacity is equal to the partial molar derivative of internal energy with respect to temperature. All right? And so that's where this comes from. In any case, inside this differential, we know that from our material balance that the mass is constant. And for the heat capacity, there's no information telling us that it's a function of temperature or anything. So let's just assume it's a constant as well. And so we could pull both of those things outside of the differential. Temperature, though, that's definitely changing as a function of time. So we're going to keep that inside the differential. Okay? So that's the left-hand side of our energy balance. On the right-hand side, the heat that's we need to care about is the heat that's going from the gas to the cylinder itself. Okay? And there's going to be a negative sign on here because this is an output. This is leaving the system A. This is leaving the gas and going to the cylinder. All right? So we have that negative sign there. That sign's important. And we just plug in the QAB equation that we got from earlier. Okay? And so this is what our energy balance for system A is. And I'm going to call this equation 1. Let's now work on the energy balance for system B. Once again, we start with the rate form. We don't care about changes in kinetic or potential energy. We don't care about changes in work, or there is no work, so that also goes to 0. So our energy balance reduces down to the change in internal energy of the cylinder, system B, is equal to some sort of total heat. For the internal energy, we could apply the same approach that we used for the gas, where we replace the internal energy with its definition from the heat capacity. And just like for the gas, both the mass and the heat capacity are constant. So we could take those outside of the differential, but we keep the temperature in the differential. For heat, there's 2 heat components that we need to deal with here. Okay. There's the heat that goes from the gas to the cylinder, right? So that was QAB. And in this case, it's going to be positive, right? Because this is going to be going from system A to system B. So this is going to be an input. Right? The other heat we need to consider is the heat that goes from the cylinder to the surroundings. Okay? And this heat is leaving the cylinder, so this is going to be a negative because it's an output. Okay? And so those are the signs of the 2 different heats, and so when we plug in for them, we get positive HA TA minus TB, and then minus HA TB minus T naught. Okay? And so this is our energy balance for system B. Okay? So we have the energy balance for the gas and the energy balance for the cylinder. And now I want to rewrite them for a bit. Just kind of arrange them so that they're all together. Okay? And so for system A, we have dTA d time. And what I'm doing is I'm going to divide the mass of system A and the T capacity, divide the equation by that. So what we end up with on the right-hand side is HA, MA, CVA, TA plus HA, MA, CVA, TB. So once again, this is just equation 1. And then for the cylinder, I'll do similar sort of thing. I'll divide both sides of equation number 2 by MB, CVB. TA minus 2HA, MB, CVB, TB plus HA, MB, CVB, and then T naught, which is that T of the surroundings. Okay? So we have these two differential equations, right? And we could see that they're coupled. dTA not only has TA in here, it also has TB. And it's the same thing with our second differential equation. Okay? And so essentially we have a system of coupled ordinary differential equations. And here, we wrote it out like this. But another way we could write out these two equations is we could write it out in matrix form. And so what we have is d dt, and then if I draw this big bracket, we have TA, TB is equal to negative HA, MA, CVA, HA, MA, CVA, here, positive. On the bottom, we have HA, MB, CVB, that's a positive value. Here, it's MB, CVB, it's negative. And then this will be plus 0, and HA, T naught, MB, CVB. Okay? And so in matrix form, all we're doing here is this first column is all the coefficients that are multiplied by TA. The second column here are all the coefficients that are multiplied by TB. And this vector we have after the plus sign, these are all the constants that are added onto the equation. And so that's how we're writing it in matrix form. Okay? And a more compact way to write this, or just in general when you are dealing with a system of ordinary differential equations, is you could write it like this. Oh yeah, I guess I should write what I forgot. TA and the TB here. Okay? And so in this way, this thing over here, this is Y. This matrix here is A. This is Y again. And then this is our B vector. Okay. All right, and so in general, if you have this sort of system of ordinary differential equations, you could solve it using or by calculating the eigenvectors of this of the A matrix, right? And so that's how you solve the bonus problem 6 on homework 1. Okay? So that's how you would approach that bonus problem. Of course, calculating the eigenvectors of the system of ordinary differential equations can be a bit involved. And so what I want to do is, in order to develop some physical intuition about how heat transfer would work in this sort of system, what we're going to do is we're going to explore specifically some limiting cases. Okay? And so to develop some physical intuition about heat transfer, we'll look at limiting cases. And so this is a common thing that's done in engineering and physics whenever you're dealing with a really complex system. Okay? So we're going to look at some limiting cases. And so in part B, one limiting case we could look at is when mathematically the product of MB and CVB approach infinity. Okay? And so when that happens, if we take a look at equation 2, we take the limit of it as MV, CVB go to infinity, what we have is dTB dt. If we write out our equation again, since we have MBCVB in the denominator in all of these terms, if we take the limit as it goes to infinity, 1 over infinity is equal to 0. So we get that dTB dt is equal to 0. Okay. We could bring the dt to the right-hand side, and when we integrate that indefinitely, we get this, where alpha here is just some sort of constant. Okay? Alright, and to figure out what that constant is, we could apply our initial condition. We know that TB is equal to T naught, time is equal to 0. Therefore, TB at t equals 0 equals T naught, which is equal to alpha. And so that just means that TB is equal to T naught, which is a constant. Okay? So mathematically, if we assume that this product of MB/CVB approaches infinity, we get that our temperature of the cylinder just stays constant. Okay? So mathematically, that's what the equation reduces down to. But now let's think about physically what this would mean. Okay? Why did we look at a limiting case? Why is it useful to look at the product of MB/CVB? Okay. And so in general, a mass or a molar amount times a heat capacity, we describe that as the thermal inertia of a system. Okay? And so this thermal inertia, just like how the way you learned about inertia in your physics class is the resistance of a system to change its speed. When we talk about thermal inertia, this is the system's resistance towards changing its temperature. All right? So that's what that product essentially represents. And for it to be equal to infinity, there's kind of two different ways that could happen. The first way would be if the mass of the system approaches infinity. And what would that mean? Right? And so if the mass of the system, of the cylinder specifically, approach infinity, the way you could think about that is that relative to the gas, there's just a lot of B molecules. Okay? And there's so many B molecules that when the microscopic energy transfers from the A molecules to the B molecules via heat transfer, only a few of those B molecules are actually affected, so that the average temperature of the B molecules overall basically stays the same. And so when we have this, when this happens, we essentially say that system B acts as a thermal reservoir. Right? And so the concepts of thermal reservoirs, these are going to come up quite a bit in thermodynamics. Okay? And so if the mass of the system is infinity, that just means your system is very big relative to the gas. The cylinder is very big relative to the gas. The other way that our thermal inertia could be infinity is if the heat capacity is infinity. And so this would mean that it takes a lot of energy to change 1 gram of the system by 1 degree Celsius. And so in this case, if your heat capacity is very large, what you essentially have is an insulator that's very good at maintaining the temperature of that specific system. Okay? And of course, not only could MB or CVB individually be infinity, but you could have both of these things be true as well. You could have a large thermal reservoir of an insulator. Either way, your thermal inertia would be infinity. Okay? All right, and so physically that's what this means if MB CVB is infinity. And based on this, we could solve for T naught. Now that we solved for T naught, we could go back to the differential equation for the gas. Where now we could replace TB with T naught. Okay? And then, this is a separable differential equation. And we could integrate this indefinitely. And then time is here. And then we also have another integration constant, since we integrated this indefinitely. Also, just to remind you, when you have 1 over temperature, your integral ends up being a natural log. So make sure that whenever you get integrands in this form, that you integrate it correctly. Okay? Alright, but now we need to figure out what the beta constant is, and we could do that by once again applying our initial conditions. So we know that the gas is at some initial temperature Ta naught, at time is equal to 0. So when we apply that initial condition, HA, MA, CVA times 0, because it's at time 0, plus beta, right? We get that beta is just equal to this. Okay? Alright, and so what we now have is ln of Ta minus T naught is equal to minus HA MA CVA times time plus the natural log of Ta naught minus T naught. And if we rearrange this equation, which I'll do on the next page, we get that Ta is equal to T naught plus Ta naught minus T naught times the exponential of negative HA MA CVA times time. Okay? And so what we get here is that the temperature A is going to decay exponentially. Versus time. Okay? And so if we plotted temperature of both the gas and the cylinder as a function of time, we would develop curves like this. So for the gas, it starts at Ta naught, and then it's going to decay, or this term will decay exponentially until it's basically 0, and then the only thing you'll be left with is T naught here. So, got to decay. Oh, let me draw this a little bit sharper. You'll get something that looks like this. Alright, for TB, it's just a constant when we make the assumption that thermal inertia is high. You know, it's a thermal reservoir, so it's just going to stay at one temperature. So we're staying at T naught, and we're going to continue off. It's just going to be a flat line. Okay? So graphically, this is how the temperatures would change in our system. Another thing I want to point out is inside the exponential, you know, we have time here. We also have this kind of collection of constants. And if you did the dimensional analysis on this collection of constants, you would see that their dimensions would be 1 over time, which is necessary, right? Because time here has dimensions of time, and inside the exponential, that product needs to be dimensionless, okay? And so it's important that this collection of constants has units of inverse time. On the flip side, though, that means that if you took the reciprocal of that ratio of constants, it would have dimensions of just time. Right? And so, because of this collection of constants that we have here, we typically refer to it as a special name. So we could abbreviate it as tau of A, and I'll call this tau of A part B. And we call this the thermal decay time. Right? And physically, what it represents is, if you look at the numerator, we have our thermal inertia, our MACVA. And in the denominator, we have our heat transfer coefficient times area. And so what this decay time is comparing is just the ratio of thermal inertia over the rate of heat transfer. Okay? And so the way to think about it is, if the thermal inertia of the system is larger, much larger compared to the speed of heat transfer, your tau A, your thermal decay time, is going to be very large. And if it's very large, the reciprocal of it is going to be very small. And so that would mean that your system would take much longer to actually decay towards its equilibrium temperature. Okay? Because, once again, thermal inertia is so high, it takes a long time for that system to actually change its temperature. On the other hand, if heat transfer was much more significant than thermal inertia, then your tau A would be very small, its reciprocal would be very large, and that would mean that your system's able to change temperature really quickly, and so your decay would be much sharper. Right? And so it's very useful, not only in the context of this problem, but also in the context of just engineering in general, to try and find cases where you could define some sort of decay time or things like that, because they could help give you some insight into the behavior of your system. All right, so for part B, we looked at the case where our thermal inertia was approaching infinity. Let's now, for part C, look at the opposite case, the opposite limit, where our thermal inertia is going to be very small. So small that we could just say it's 0. Okay? And so in this case, mathematically what we would do is we would take equation 2, but we would take the form in which the dTB dt, we take the form where it was multiplied by MB CVB. Right? And we would be taking the limit as the thermal inertia goes to 0. Okay? And so our equation would look like this: 2HA TB plus HA T naught. And if we're taking the limit as this goes to 0, this is 0. And so this whole equation would just be equal to 0. Okay? And so what we end up with is an algebraic equation that we could then just solve for TB. And we get that TB is equal to TA plus T naught, all of that divided by 2. Okay, so mathematically that's just what happens. Okay, now physics-wise, what does this mean? So we're looking at the case where thermal inertia is very small. And the reason that you could get that sort of behavior is if MB was very small, basically approach 0. And so the way to think of that is that you only had a few B molecules relative to the gas. The cylinder was very thin or very small, so that you only had a few B molecules that you needed to heat up. So here MB approaches 0. Okay. The other way would be if CVB were very small. And so if that were the case, we would say that the cylinder was a conductor. So the opposite of an insulator. So this would be if CVB were 0. Well, and of course, both things could be true as well. Okay? And as a result, the consequence of this is if the thermal inertia for the cylinder is very low, that means heat transfer through the cylinder is very fast. And if the heat transfer is fast, what ends up happening is that your system B, or the temperature of system B, just ends up being the average of TA naught and T naught at any given moment, or time point. Okay? Alright, and so that's, what the math is telling us. TB is just TA naught plus T naught, all of that divided by 2. Of course, I want to emphasize the reason we got this simple equation is because we assumed all the areas for both the AB contact area and the B surroundings contact area, we assumed those were equal. But that may not be the case. In fact, in the actual homework problem, that is not the case. And so your equation is going to end up a little bit different. Okay. In any case, for our system, we ended up with a very simple equation for TB. Now that we have that, we can go back to the differential equation for TA. We could plug in our result for TB. HA, MA, CVA, TA divided by 2, minus T naught divided by 2. Okay. And we solve it basically using almost an identical approach that we did in part B. So here we get this. dt. So follow same steps as part B. Okay. And if we go to the next page and you follow those same steps, what you get is TA is equal to T naught plus TA naught minus T naught times the exponential of minus HA divided by 2 MA CVA at times time. Okay? Alright, so this looks almost the same as the answer we got for part B, except now we have a 2 here. Okay? If we plotted the temperature versus time again, so infinity, this is 0, this is TA naught, this is T naught. For the gas temperature, we still have an exponential decay, but it's not as shallow, right? And I'll talk about what that means in a bit. So it's not as shallow. For the B temperature, it's a little bit more interesting. And so what we have is that time is equal to 0, it's still equal to T naught. But as soon as we jump up by 1 second, the temperature will jump up. Or not even 1 second, just as soon as the temperature is not equal to 0, it's going to jump up immediately to be the average of TA plus T naught divided by 2. And then, since TB, which I'll write again here, is this, or essentially it's TA divided by 2 plus T naught divided by 2. This is a constant, and we know TA is an equation that decays exponentially. And so TB will also decay exponentially as well, right? And the entire time, once again, it's essentially just going to be an average of TA and T naught. And so TB will be in between the two. Okay. The other thing I want to point out is, once again, this, or the reciprocal of this, to MA CVA over HA. We could think of this as a thermal decay time for part C. And everything is the same except there's just a 2 here, right? So this one's actually just twice as big as the answer we got for part B. Or essentially, it's saying this decay time is twice as long, okay? And so the way to think about it here is it takes twice as, for the case where we have a fast heat transfer, or the thermal inertia for the cylinder is very low, it takes twice as long for the gas to actually cool down, for it to actually get down to T naught in part C than it did in part B. Okay? So it takes twice as long for the system to cool down than in part B. Okay? And so once again, that's why it's kind of useful to think of things or do the dimensional analysis and find opportunities to find these sorts of constants, right? Because once again, this thermal decay time is just a ratio between thermal inertia and heat transfer. And so in part C, it's telling us that the thermal inertia is twice as significant in this situation than it was in part B. Okay? All right, and so we looked at these sort of limits. We looked at these limiting behavior to kind of just develop some physical intuition about the system. But in some, these are all like idealized sorts of things, right? There may not be actually representative of the real system. In fact, here, the temperature we get for part B, it's kind of weird, right? Because it starts at a low temperature, spikes, and then goes down immediately. And so for an actual system, for an actual gas, if we had this sort of setup and did this sort of experiment, we looked at the limits, the two extremes of behavior. And so for a real system, we would expect something that's in between those two limits. Okay? And so if we plotted the temperature versus time, infinity, here's TA naught, here's T naught, okay? We'd probably still expect temperature A to follow some exponential decay, though the rate at which it decays would be a bit different. And then for temperature B, what we would expect is that rather than staying constant the entire time or having a sharp spike, we would actually just probably expect a more gradual spike. So there'd be some sort of maximum in the temperature, and then it would follow that exponential decay. Okay? And so the way to actually, develop a equation to model the real system is you would actually have to go out and solve the eigenvector problem.